Somewhere in the southern sky, too faint for your eyes to ever find, there is a star quietly doing something it should not be able to do. It is making elements that cannot last, metals from the very bottom of the periodic table, the radioactive basement where everything falls apart in years, not eons. By every rule we know, those elements should have decayed to nothing long before the dinosaurs, long before the Earth had oceans. And yet, when astronomers spread this star's light into a rainbow and read it, line by line, the elements are there. Right now, burning their fingerprints into the starlight. It has a name, a hard Polish name that most people never learn to say. And for 60 years it has sat in the catalogues as the single most chemically bizarre star ever found. A thing that looks, for all the world, like someone built it wrong. This is the story of Przybylski's star. And the unsettling part isn't that we can't explain it. It's that one of the explanations written down by serious scientists is something nobody wanted to say out loud. Start with how ordinary it looks. HD 101065. A dot in the constellation Centaurus about 356 light-years from here. In cosmic terms, that's nothing. That's our own backyard. It's a small star, a little heavier than the sun, a little cooler, around 1.5 billion years old. Through a telescope, it isn't even a respectable point of light. At magnitude 8, you can't see it without glass. If you swept right across it on a clear night, you would never know. Nothing about the dot warns you. The warning is hidden inside the light itself. And to understand the warning, you have to know how we read a star at all. We have never touched another star. We never will. Everything we know about what they're made of, we know from one trick. When you split a star's light into its colors, you don't get a smooth rainbow. You get a rainbow with thin, dark gaps cut into it like a barcode. Each chemical element absorbs its own exact set of colors, and so each element carves its own pattern of dark lines. Hydrogen leaves one signature, calcium leaves another, iron leaves thousands. Read the barcode and the star tells you its recipe without you ever leaving the ground. It's how we learned the sun is mostly hydrogen, and it's the closest thing astronomy has to a fingerprint. In 1961, an astronomer named Przybylski pointed a spectrograph at this faint southern dot and read its barcode. And the barcode made no sense. The first thing wrong was what wasn't there. Almost every star you can name is full of iron. Iron is the ash of the cosmos, forged in dying stars and scattered everywhere, and it stamps its dense thicket of dark lines across nearly every stellar spectrum we own. Our sun has it. The next star over has it. It's the background hum of the galaxy. Przybylski's star is missing it. The iron lines that should dominate the spectrum are faint to the point of nearly vanishing. By measurement, this star holds less than 1% of the iron the sun does. For a while, astronomers genuinely argued about whether some of those iron lines were present at all. Picture that. A star that looks like someone reached in and scrubbed out the most common metal in the universe. That alone would have made it strange. But the missing iron was only the empty space. The real shock was what had moved in to fill it. Where the iron should have been, there was a flood of the exotic, the rare earth elements, the lanthanides, the strange middle row that hangs off the bottom of the periodic table, the elements with names like praseodymium and neodymium and holmium that most of us never think about. In Przybylski's star, they are not just present, they are overflowing, enriched by a factor of around 1,000 over what the sun carries. Some of them are so abundant here that this dim, faraway star became one of the best places in the sky to study them at all. So this is a star with the contents of a normal star turned inside out, almost no common metal, a drowning excess of the rarest. By the 1970s, it was the most chemically peculiar spectrum known to astronomy, and it has more or less held that title ever since. If the story stopped there, it would be a curiosity, a weird recipe, a footnote. It didn't stop there. In 2008, it got an order of magnitude worse. That year, a team led by the Ukrainian astronomer Valentina Gopka went back through the spectrum looking for the heaviest elements of all, the actinides. The bottom shelf of the periodic table, the radioactive heavyweights, and they reported finding them. Not one or two, a whole sequence: actinium, protactinium, neptunium, plutonium, americium, curium, berkelium, californium, and, sitting in the data like a lit match in a dark room, einsteinium. These are not elements you find lying around the galaxy. Several barely exist on Earth outside reactors and the debris of nuclear tests, the elements of weapons and warning symbols, and the spectrum of this quiet little star 356 light-years away appeared to be laced with them. To understand why that single sentence sent a quiet shock through a corner of astronomy, you have to understand what radioactive really means. Radioactive elements have a clock built into them. They fall apart. We measure that falling apart with a number called the half-life, the time for half of a sample to decay away into something lighter. And for these elements, the clocks are brutally fast. Einsteinium's longest-lived form lasts a little over a year. Promethium, around 17 years. Even technetium, the most patient of the suspects, gives out after a few million years. Hold that against the age of this star, 1.5 billion years old. If einsteinium had been baked in when the star formed, its clock would have run through roughly 1 billion half-lives by now. There would be nothing left to find. The elements should be long gone, beyond any hope of detection. But the light says they're there, and that forces one genuinely disturbing conclusion. If those elements are truly in that atmosphere, they cannot be original. They cannot be old. Something has to be making them or delivering them more or less continuously, right up to the present day. A star is not supposed to be a factory for elements that don't last. So what is going on inside this one? Over the years, scientists have offered 4 answers. They run from the reassuring to the frankly unnerving. The first answer is the calm one, and probably the most respectable. Remember how still this star is. It has a powerful magnetic field, thousands of times stronger than the sun's at its surface, and it barely turns. While our sun rolls over about once a month, Przybylski's star takes something close to 200 years to complete a single rotation. It is one of the most motionless stars we know. No churning, no mixing, a surface held perfectly, eerily still. In that stillness, a delicate sorting can happen. The pressure of the star's own light can lift certain elements upward, while gravity lets others sink. A slow separation called radiative levitation. Float the rare earths up into a thin skin at the surface, and a fairly normal star could wear a freakish mask, reading as wildly peculiar when it's only sorted. This idea works beautifully for the rare earths. It is the mainstream explanation, and it's likely a real part of the answer. But notice what it doesn't touch. You can float an element up to the surface. You cannot float up an element that no longer exists. Levitation can rearrange what the star already has. It cannot manufacture fresh einsteinium. For the radioactive part of the mystery, the calm explanation simply runs out. So the second answer goes looking for a source. Gopka's own team suggested one. What if Przybylski's star isn't alone? What if it has a hidden partner, a neutron star, the ultra-dense corpse of a dead sun, orbiting close and showering the surface with freshly forged heavy elements? It's a clean idea. Neutron stars are exactly the kind of furnace that can build heavy atoms. A companion would give you a steady supply, made now, not billions of years ago. There's just one problem. We've looked, and nothing's there. No neutron star has been found orbiting in the kind of tight, fast partnership the idea needs. You can't build your explanation on an object that refuses to show up. So the hidden companion stays exactly that, hidden and unproven. The third answer is stranger, and it reaches past the edge of the known. Our periodic table is not finished. Physicists have long predicted that somewhere out past the heaviest elements we've made, there may be an island of stability, a cluster of undiscovered super heavy elements that, unlike their crumbling neighbours, could survive for a very long time. Elements that aren't on any classroom wall because no one has ever held one. In 2017, the physicist Vladimir Dzuba and his colleagues put forward a possibility. What if Przybylski's star is full of those? What if it carries long-lived super-heavy elements from the island of stability, somewhere around element 114 or beyond? And what we're seeing as plutonium and americium and the rest is simply the wreckage. The daughter products. The lighter pieces those unknown giants leave behind as they slowly come apart. If that's true, this faint star isn't just chemically weird. It's a natural laboratory holding a piece of the periodic table we have never seen, decaying quietly in plain sight, 356 light-years away. A new chunk of chemistry, hiding inside one star. And then there's the fourth answer, the one that gets whispered, half as a joke, by people who absolutely should know better. Back in 1980, two scientists, Daniel Whitmire and David Wright, published a paper in the journal Icarus, then edited by Carl Sagan. It asked a single strange question. If an advanced civilization had a nuclear-powered industry, what would they do with the waste? Their answer: throw it into your own star. Use the star as the ultimate incinerator. Do that, they argued, and you would slowly change its spectrum in a way another civilization, light years away, might one day notice. They even worked out which stars would show it best, and which elements would be the tell. The signatures they predicted were praseodymium and neodymium. For decades it was just an idea, a thought experiment about how you might spot someone else's technology written into starlight. Then people looked at Przybylski's star. It sits close to the exact type of star the 1980 paper said would work best. And among the rare earths flooding its spectrum are praseodymium and neodymium, the precise elements the nuclear waste model called out 40 years early. Astronomer Jason Wright revisited the whole tangle in 2017, and the star has been called, only half-jokingly, the best stellar candidate for alien technology we have. Not proof, never proof, but a coincidence strange enough that serious people keep it on the table. And here, if this were one of 100 other videos, we would stop. On the aliens. On the chill. But the honest version of this story has one more turn, and it cuts the other way. In the last few years, astronomers have gone back to the spectrum with fresh eyes, and they couldn't confirm some of the most famous claims. Recent analyses could not verify the technetium or the promethium that helped make this star a legend. The trouble is the spectrum itself. It's so crowded with overlapping rare earth lines that hunting for one element in it has been compared to finding a needle in a haystack made of needles. Some of the impossible elements may not be impossible at all. They may be misreadings, ghosts in an overcrowded barcode. As of a review published in 2026, the case is still open, and quietly so. No one has truly closed it, and almost no one is looking. The most likely honest answer is the dull one, a strangely calm star sorting its own rare earths, plus a handful of contested lines we haven't pinned down. Probably not a neutron star, almost certainly not aliens. Probably. But sit with what that probably admits. This is not a quasar at the edge of the observable universe. It is not some object so far away the light left before Earth existed. It is a single star in our own galactic backyard that appears to break the periodic table. And our honest position in 2026 is that we don't fully know why, and we have barely looked in decades. We build telescopes to photograph galaxies 13 billion light-years away. We map the cosmic microwave background to a fraction of a degree, and 356 light-years from here, practically next door, a faint star has been quietly printing elements that shouldn't exist into its light for as long as we've been watching, and we let it sit, half-examined, in a catalogue. The unease of Przybylski's star was never really about aliens. It's about how much of the sky right above us we've never bothered to read. It is still up there, still turning almost imperceptibly once every couple of centuries, still ringing every 12 minutes like a struck bell, still burning those impossible lines into the starlight, whether or not a single telescope is pointed its way, whether or not we ever work out what it's telling us. A small, strange star keeping its secret in plain sight, waiting for someone to look closely enough to finally read it. This is Nightside,